Just before I begin, maybe a short biography fact. The last time I was in Moscow was 29 years ago, and I'm very excited to be here again, even if it's just a virtual presence. So let's begin applying the hourglass in library design. So even before I start with the problems, motivations, solutions, hopefully, I want to give credit to people that also talked about hourglass, or at least about the problems that it solves. And all these are available on YouTube. You can watch them. They cover some aspects that I simply don't have enough time to talk about. David's talk is in Spanish, but it is also the most aligned to my talk, and it's fine to skip. I actually talked to David. I gave him a training talk, and he gave me his seal of approval for this one. All right, so let's see how it's going to work. There's going to be introduction, a pretty long introduction of the problems, the motivation for this. I'm going to talk about API compatibility and then ABI compatibility. And then I'm going to introduce the hourglass as a concept, a pattern, a paradigm. And following is a detailed discussion with all sorts of details that has devil in them, usually. All right. So what is the problem? Imagine you need to ship a closed source library to clients that you do not control. And by you do not control, I mean the following. They may be using different compilers than you are when you're building your library, uh, even if you're on the same platform. And they may be using very different standards of C++. They also quite reluctant to update your library for all sorts of reasons. There are those anecdotal companies that still use COBOL, especially in financial business. Those people are our clients and they're not updating often. And the most interesting bit, and the most troublesome for us at least, is that quite often they don't even have the source code for their application. The way it works, they hire a third-party vendor, and this vendor is going to write code against our SDK, against our library, which means that even something as trivial as recompiling with new headers is going to cost the client money because they need to go to the third-party vendor to do it. Okay. All those pretty much lock us into a model where we have to use DLLs or shared objects. They cannot be statically linking if we want to allow them to make updates without recompiling. Recompiling is not something they like to do. If you give them a new DLL, they drop it and deploy it. It's acceptable in some cases. So what are the things that happen usually? So imagine they have a client and they build it against a certain version of our library, 3.14, for example. And when they build it with a certain set of headers, 3.14 headers. All is fine and great. Now 3.14 is basically 3.13 plus some new features. We decided to optimize a bunch of algorithms. They were linear and now they're log n. And the client wants to be able to use it. Everything is good. As it often happens, you introduce a bug when you write a new feature. So the client can safely revert to previous version by just replacing the DLL with the old one. Their application is still compiled against 3.14 headers. It should be fine. In order for it to be fine, we need to do all sorts of things, and the next 50-ish slides are going to talk about this. Then, of course, we fix the bug, we introduce a patch, and they drop in the patch with the same client, everything works. Time goes by, we add even more features. This is 3.15, and they still use 3.14 headers, nothing changed, everything is good. And up to a point where we introduce a change that is so important to them, and the change is also in the public side of the API, that they must recompile. It's either that or they don't get the new feature. At which point they say, okay, fine, we're going to recompile, we're going to bite the bullet, pay the price, and they do it. Okay, so now we're kind of aligned again. And in general, we like to have a strong guarantee, even if it costs us in some, well, cumbersome code, as you're going to see. And the strong guarantee is it doesn't really matter with which version they were compiling. They can run with any version we give them. And if it's one direction, if it's x less than y, this is going to work because we promise not to introduce breaking changes on the API level and also on the ABI level, as you will soon see. And in the other direction, it's also going to work as long as you're not using any new feature. So imagine if there is a new method, you cannot call it because it wasn't part of the header. But otherwise, everything else is going to work. If all your changes are in the invisible private part, changing data structures, making better algorithms, it's all fine. Okay, so let's talk briefly about API compatibility, which is important to us library developers. And this is only for classes that are publicly facing. And these are the things that our client's compiler is seeing and compiling. So you are not allowed to do many things. You're not allowed to rename namespaces, classes, or methods, because if you do, they have to recompile. This is an API compatibility breaking change. Changing signatures of functions or methods is also no-go, including changing return types, including changing CV qualifiers, template arguments. You cannot change them, of course. Adding new overloads is fine. In general, adding new things is okay, because if they don't have them, they don't know they're missing them. And if they recompile, they get the new stuff. Similarly, you cannot change which exceptions you throw in your code and whether you throw them. You cannot change types of globals. You cannot make public things private suddenly. And there is a long list, you can imagine. All those things, the moment you do them, there is a breaking change in APIs, they have to recompile. So if you're in the habit of doing this every version, there is very little that I can do to help you. So everything else that I'm going to talk in the Hourglass in the next 50 slides is not going to help you if you force your clients to recompile. In fact, if you are able to make them recompile often, probably you don't need the Hourglass. It introduces certain overhead and it makes your code slightly uglier than it already is or isn't. Well, your mileage may be different. Okay, so let's go to the next level. Imagine that you're fine, you're not changing API, you're only adding new things and you never deprecate a function because that would break clients and would break them in a sense that would make them recompile. There is still the issue of ABI. So ABI is a binary interface. This is what your compiler generates from your high-level nice code. This is the machine-level instructions. It's essentially a set of conventions, how functions are called and returned from, including system calls, how arguments are passed to those functions, what is the data layout for structures, how stack is managed, etc., etc., etc. So each compiler usually comes up with their own set of decisions. The sad thing about ABI is it needn't be the same for different compiler on the same platform. So for example, Visual Studio's different versions weren't binary compatible with each other's. Namely, if you have object file built in one and object file or DLL built in a different version of Visual Studio, you didn't have any guarantee about calling functions of one from the other. It's getting better, but it's still problematic. So different compilers, different versions of the same compiler, and occasionally even same compiler but with different compilation flags. All this could produce a different conventions and thus make your two parts binary incompatible. Okay, so let me give you an example. We still support all sorts of funny platforms like Sun, Solaris, and IBM AIX, and some more standard like Windows and Mac OS, etc., etc. If on Sun Solaris we build our library with the Solaris compiler and target standard 03, and our client want to build on Solaris with GCC and target C++11, the first part, the include of the header, is obviously going to work. And they're going to see std string and assume we're talking about the same std string. But of course, it's not the case. The std string in our library is going to be very different in all sorts of funny ways. And then any string method or even construction of string is not something you can do if you're a client that builds with a different ABI. All right. So what are the breaking changes in terms of ABI? So imagine that you did manage to somehow avoid API changes. You can still sneakily introduce a change into ABI. So adding or removing or reordering member variables in a class is a breaking change. Because as I said, ABI has to deal with layout of structures. If you start reordering things, the layout changes, and then two versions compiled differently are not going to be able to call to each other. You break conventions, you break contracts. Changing the types of member variables in a class is bad. Adding an explicit copy constructor or destructor when there was none and it was generated for you is a change. Inlining a function or a method is a very sneaky way of breaking ABI, and it's sneaky because you don't see it unless you have a habit of checking your object files, assembly, etc., etc. And this is also an example of how modifying compiler flags can cause a breaking change in ABI. There was a calling convention, and now there is no call at all, and there is no return, and the arguments are not passed. Okay. C++, right? We love our virtual inheritance. So almost anything that has to do with the change of a class and deals with virtualness is going to be a breaking change. So making something virtual when it wasn't or vice versa is a breaking change because the layout changes. You introduce a virtual pointer in your object. Adding virtual methods to non-virtual class. Similarly, removing virtual method modifies that particular table. Changing the order modifies a particular table, etc., etc. And again, the list of ABI break-in changes is also pretty long. We're not going to cover them all. So the question stands, is there a way to have a standard and stable ABI? So I compile something on my side, you compile something on your side, and we can still talk to each other? Well, there is one, and sadly, the list only contains one item at this point, and it is C. And because we have all the funny platforms, we are quite conservative. We use C89. You can probably get away with C99 when you need to. This means that if your code is C code, you can compile with any compiler on your platform and they will be binary compatible. Function calls will succeed. You will not get undefined behavior. And if you're in the C++ way of thinking, then anything you put inside extern C is going to be by your compiler made compatible with C layer, and all the calling conventions and layout convention are going to be C conventions. Now, if we were to do something like that, we have const char star name. This is a C function for all intents and purposes. It's an extern C. So when we build our own library with Sun Solaris compiler, it's going to provide the same ABI calling convention for this function as GCC C++11 that our client is going to use later. And when they make the calls or construct things, it's going to work. Okay, fair enough. Now, there are, of course, certain scenarios where you are lucky or you're in a niche case. So, for example, gaming consoles. Normally, you have a very stable platform and you have a stable C++ ABI because the vendor will lock you into a particular compiler and particular version. Another scenario where you can get a C++ stable ABI is embedded, for example, because you have just one compiler and that's it. In every other case, you have to go back to C, which is a bit unfortunate. So the whole reason of the Hourglass is to try and make it more pleasant and yet more safe. So here we go, the Hourglass Principle. It means you introduce a scene layer of C calls and everything goes through C calls because that's the only thing we can do conservatively. It's the only thing that will work for any compiler on this platform. And then your implementation of C++ classes is going to be hidden in the private layer, and you're going to give users a C++ public interface for them to use. Okay. So the shape looks like an hourglass. This is how the industry and the community call it. I would call it an X-wing, but too late. If we were to scale this picture, it's something like that. Most of the things are, of course, inside your CPP. This is the rich C++ private implementation, all your classes, etc. And there is a relatively thin C++ public interface, and all it does is inline calls to the extern C functions that are declared there and implemented below. Now, if you go through the burden of doing the Hourglass, there is a bonus. I would like to mention it now because I have no other opportunity to mention it later. If you did it like that, porting your library is extremely easy because you already have the C layer. So any language that supports calling C functions can be a port. So it can be Ruby, Python, Node.js, Rust, whatever you want. Now, just to make another point, in this slide, you may see that the C++s are color-coded. This is to make sure that you remember they needn't be the same C++. It can be different compiler, different standard, our own libraries that we use instead of std string, etc., etc. This is the problem. Because they're not the same, we need to do it like that. All right. So this was the introduction, and now I want to show you some examples and then go into more detailed discussion. From here, you will see way more code on the slides. Don't be alarmed. All the code is available on GitHub. I will send, there is a slide with the link eventually. So you will be able to see all the examples. They're compiling and running. Okay, imagine you have an existing class and you want to use the Hourglass principle because this class is going to be used by your clients and your clients will use a different compiler. So let's Hourglass it. This is a simple class, as simple as it gets. It's some sort of profile implementation. It has a name and age. And again, I'm saying my string, not necessarily because we have our own implementation of string, although we do, but because our std string is not like our client's std string. All right. So the first thing we do is to introduce an opaque handle. This struct profile T declaration doesn't mean we can construct profiles. We cannot instantiate it, this thing, but we can use it to pass pointers. Okay. Very simple, doesn't cost us anything. Very explicit, good name. I'll show other reasons to use opaque handles later. And then this is the C layer. If you look at it, it's basically constructor, destructor, and copy constructor. So we shed all the C++ from our class and go back to before C with classes, where everything was done in C. And if we were to annotate things, create is going to allocate memory for the profile and initialize the profile. And then it's going to populate the output argument handle and put the pointer to the profile there. And you don't give us a string, you give us const char star and the age as integer. We also return codes because there are no exceptions in C layer. And finally, if you allocate, you need to remember to delete. So you are now the owner of this profile through this pointer, so make sure you delete it eventually. Okay, and again, why use profile underscore t? Why not use void star? There are multiple reasons, and some of them I'm going to talk later, but A, it's very explicit. B, if you have more than one void star pointer in a function signature, it's very easy to mix them, and uh, you can do pretty printing in debugger, and there are other reasons that we're going to discuss later. Okay, so this is the C layer. We declare these signatures in the public side. As you can see, they're entirely C. There is nothing C++ about them. And when they're inside extern C, they're going to have calling conventions that are binary compatible anywhere. Okay, we don't want our users to write C code if we can avoid this. So we introduce RAI wrapper. This is the profile class that our users see. And it has a private pointer to the handle. And then all the normal method, constructor, copy constructor, destructor, and assignment move, whatever you think is needed there. And at this point, we say std string because this string is the one that our clients use. It's totally fine. It's not our string. All right. And as I said, the implementation of this profile is going to be inline and totally in terms of the C layer. So we say we're going to try to create a profile and populate our handle, and we're going to convert the given string to const char star. And if the return code from profile create wasn't good, then we're going to throw an exception. Similarly, in destructor, we're going to call destroy. And if the return code wasn't good, we do whatever we do when destructors have problem. Normally, you don't throw, you can assert, you can write to log, etc., etc. And similarly, a copy constructor is going to call copy, and that's it. So pretty obvious. You have no idea what's going inside, and all the calls are C calls, which means you are always allowed to make them. How do you implement the C layer? Well, again, the C layer is pretty straightforward. It will just call the appropriate functions methods of profile impl. So create is going to allocate a new profile impl. It's going to be a heap profile impl. It's going to construct a new string from the const char star that was given to us. And then it's going to reinterpret cast it to this opaque pointer and store it in the handle that the user gave us. So now the user is a private owner of a profile impl that was type erased and now called profile underscore t. When we do destroy, we go in the other direction. We cast it to profile impl and then delete it. And then the destructor of profile impl is called and everything is good. This is not something the user sees. This is all in our private side. And the copy is similar. We're going to invoke the copy constructor of profile impl and populate destination with this address. Now, if we were to map a constructor, for example, onto the Hourglass, it would look something like that. On the public side, the ones that C++ of our users see is profile constructor and the declaration of profile create, where profile constructor just calls profile create. And in CPP, in our private side, we implement profile create and we implement profile impl. Now let's imagine we want to add another method, a getter for age. We have to put this in all layers. In the public side, we will have a get age. And along with it, we will have a C layer, which is profile underscore get age. And then the implementation of get age and the implementation of the getter in our side. So this is the public side. There is a C function that, given a const profile pointer, populates an integer. Again, we always use return codes, so we have to use an output argument here. And then get age is, oh, here's an integer. Please put the age of my particular handle inside this integer. If it fails, throw runtime error, return age. Okay. So they don't see any of the mess. They get nice C++ interface. You realize there is some overhead here, and we're going to discuss it later. Okay, on the private side, you just add a getter for get age, and then you use this getter in the C function. You reinterpret cast the profile, and you get the age. Done. Okay, let's have a quick recap of what we just saw. So the how part. How did we do what we did? We used extern C to signal the compiler that the calling conventions are C calling convention. Thus, we made them binary compatible. We used opaque handles to erase type. Those are essentially void stars, just pointers that going through the hourglass. And all interactions are through C functions. Anything you can do to your object, you must do through a C function that gets the pointer to this object type erased. And if you're familiar with private implementation pattern, it's like that on steroids, with even more encapsulation and even more decoupling and hiding. All right. Now let's do a recap of what. So the what is, we need to hide all our C++ code because it's not necessarily callable by the users. Now, in the nice future when we get some standard C++ ABI, we don't have to do any of it. But there are many papers, nothing practical yet, unfortunately. So for now, we have to provide the binary compatibility more or less manually by introducing this C layer. And again, C layer is somewhat nasty, so we want to give our clients a good experience. We introduce C++ wrappers that do the right thing in terms of construction and copy and destruction of those objects via C SDK. Okay, some good practices, and this comes from stories from the trenches, things we got wrong and sometimes couldn't fix. One thing you always want to do is return an integer. Always return a return code, even if the function originally is void and doesn't throw exceptions. It may change in the future. And as I said, once you choose an API, you're not allowed to change it. And in the ABI, it is even more strict. So return type modification is problematic. Similarly, for arguments, if you can use wider types, please do. For example, you have a function that expects a Boolean flag, true or false. Just pass an integer because in the future you may want to add more flags or masks or enums. Just start with the int and you won't have any problem to extend it later. If you start with a Boolean, the only way to extend it is to introduce a new overload, make documentation, ask your users to move to the new one, still support the old one forever. It's a mess. And goes without saying, you need to unit test things, but you want to unit test the public wrappers and private implementation separately. The public wrappers are all about wiring. You need to make sure that all the wiring is done correctly. Okay, more good practices. If you have more than a dozen hourglass classes, you should be consistent in the names because otherwise you're going to get lost. Just use foo for your public classes and then foo_t for opaque pointers, foo_impl for the private side, and foo_name of the method in C layer. And now, as you remember, this is C, and in C we don't have namespaces, so you have to do your own namespacing, and you probably want to prefix all the above with something like mylibrary_. And very important, exceptions cannot go through the hourglass. If there is an exception, it cannot escape, and it cannot go through the C layer because it's just going to terminate. So you must catch them. If either you don't throw them and make sure nothing throws, or you catch them on the private side on your C++ side, and then convert them to return codes propagated through Hourglass, and on the public side they can be converted to exceptions again. On the 2014 videos, it was in my prior art slide, they have a nice RAI wrapper for exceptions that works. I'm not going to go into details about that, but just be mindful, don't let them escape. Okay, so a recap, where are we? We are more or less in the middle, but now the hairy stuff begins. We did an introduction, discussed API compatibility, the Hourglass, how it solves our problem, and other problems, not just this particular problem. There are multiple motivations to use Hourglass. Some people in embedded use it, for example. And I showed how to wrap a single class using this handle or private implementation approach. Now let's go and try to make things better in many senses. So the first thing is, if you remember our profile, it had to allocate the profile on the heap, which is not what we always want. If we have some type that is small, then this allocation is prohibitive. In some cases, we can do what we do here in ID. We call this intrusive type. If your type is fairly small and looks like a C struct, or can be thought of as a C struct, you don't have to necessarily allocate it on the heap. Instead, you can say that ID create is going to accept the core of your object by pointer and going to manipulate it. And it's the same for all the other C methods. So in this case, we have two integers. This is our ID, and we can allocate ID on the stack, and then the C functions are going to get the 2 pointers. Another thing you can do is you can come up with a ID core struct and then pass a point to ID core struct. The problem with those approaches in any case is that, well, encapsulation is clearly broken. The users can see that you have 2 integers. You are also not allowed to make any modifications. If you ever regret having them as integers, you need to reorder them. You need to add additional field. You can probably land in the ABI problematic case and essentially undefined behavior. So IDs are probably fine. They're not going to change. We use it for things like date or date time. It has day, month, year fields. They're integers. It's fine. It's never going to change. And this way you save them allocation, which is sometimes a big deal. Okay, that was intrusive. Let's at this point discuss what can go through the border, what can cross this ABI Hourglass thin layer. So everything C, all plain, all data types can be passed as arguments, char, int, float. Any pointer can be passed, including void star pointers and opaque pointers that are pointers to nothing particular. C function pointers, you can pass them through the Hourglass, but you need to be very careful. It has to be a C function pointer. You cannot create a C++ function that looks like a C function, but doesn't have the C function calling convention, and pass the pointer to it. If you do, it will probably end in some sort of undefined behavior and your program crashing somehow. Okay, make sure they are C function pointers. Strings, STD strings are no-go, but practically any string you can convert to char star this way or another, const char star normally. If we take them in as an argument, either we're going to use them in the scope of the function, or we're going to copy them if we need to store it. We're not going normally to store your char star, because who knows, maybe it's going out of scope the moment this function call ends. Similarly, return. When we return a char star from our private layer, we need to have part of contract the lifespan of this char star. So maybe it's alive as long as the object that gave it back to you is alive, or maybe you have to copy it immediately, or maybe we even don't allow this. We tell you, hey, give us a buffer and we will push the bytes of the string into your buffer. So various possibilities. And these are the easy things. Of course, the harder things are actual C++ types. So shared pointers or any smart pointer, C++ invocables, i.e. std function, lambdas, vectors or other collections. Sometimes it makes sense for you to give us a vector and we push back to it, or you give us a map and we populate the map. Similarly, streams. Occasionally you want us to stream data in or out. You cannot pass any of those through the hourglass as they are. You can of course type erase them and pass them as void star, but it's still a problem because, well, imagine you gave us a shared pointer. This is a shared pointer in your library, in your compiler, in your vendor, in your standard. We may have C++03, so we don't even have that kind of shared pointer. And even if we did, it wouldn't be safe for us to make any calls to it. So you need to use a different technique. Let's talk about shared pointers. I don't need to convince you that shared pointers are useful. Obviously, sometimes you want to deterministically manage lifetime of objects. You want to share them between layers and threads, and you want to ensure that resources are freed correctly. So shared pointers and smart pointers are great. Now, one way to do things is to allocate the shared pointers on the heap and not allow you, the public user, to realize that those are shared pointers. So they are my shared pointers. You are not allowed to call any methods, and you will see the opaque handle always. And the way we can do it is, well, you do make shared, which creates a session symbol and control block. And then you allocate the shared pointer itself on the heap, yet additional allocation. And then you populate the handle with this. So previously in profile, we just created a raw profile and said, this is your thing. This time we actually cast the shared pointer to our opaque handle. Right. In destroy, we do it the other way around. We cast it to a shared pointer session impl, we delete it, and if we happen to be the last owner, then it goes away. All right, it would work. It's not perfect because we have this additional allocation. We can do better, but not in any case. If you're using standard shared pointer, then you lack a particular ability that is there in some libraries that provide you shared pointers. And of course, if you write your own shared pointer for whatever reason, you can introduce this release semantics. What do I mean by release semantics? Usually when you have a shared pointer to something, it will have a couple of pointers. There will be a pointer to control block area. This is something that contains at least your reference count, and usually a pointer to the allocated object, and the pointer to the allocated object. Right? Release semantics is something as simple as that. You say, hey, you shared pointer, please stop being yet another owner of this object. All your pointers are now nulls. And return a pair of pointers. One is going to be the pointer to control block, and the other is going to be a pointer to the actual object. Now, if you're a holder of this pair, you are now the official co-owner or sole owner of this particular session info. So it's your responsibility to get rid of it safely. If you drop this pair on the floor, you will have a memory leak, because this particular shared pointer, when it goes out of scope, it's not going to release anything. Now, similarly, there is a way to go back. So you have a shared pointer and you construct it from the control block and so. So you have this pair in hand. You can create a new shared pointer, not on the heap, on the stack this time, and say, hey, use this control block and use this object and become the effective owner. So this gives us a solution that allows to go through the hourglass. It would look something like that. When you create a session, you create a local shared pointer. Okay? It's on the stack, the shared pointer itself, although session impl and control block are obviously allocated when you do make shared. And then you do reinterpret cast to session T of the control block. So this thing here, it spells control block, because release will give you back a pair, and we want the first thing of the pair. So this is just a type erased thing. It's a control block to anything. It can be control block to profile, to session, to foo. And when we destroy, we again don't really care what was it. We cast it back to control block and say decrement. And if you're the last one to decrement, you will call the destruction. Now again, the operating of the shared pointer is all done on our private side, because it's our shared pointer. We never give them anything that looks like a shared pointer and may confuse them into saying, oh, I can just create my own shared pointer from this shared pointer or weak pointer or anything. No, that's not how it works. All right, so two options for shared pointers. What about other things? What about lambdas? What about vectors or other collections? What about streams? So they all fall under the same category, and we have a solution for all of them. So I'm going to describe for invocables, and in bonus slides I also have streams. If we're not able to do bonus slides, then just go and check my GitHub. It will have both examples. The idea is quite simple. It's don't call us, we call you. So imagine in general you have a C++ entity, whether it is a vector, invocable, or a stream, and you want to give it to us. Now, of course, we cannot call any method on this. So along with the entity, which must be type erased, you need to provide us with some functions that knows how to operate this particular object. And in this case, we have operate function. This is a function pointer that gets an opaque pointer and arguments. And then a concrete implementation of such operator would be my op, whatever you need to do. If it's a vector, it will be a pushback, for example. And then you have use. And use, as I said, requires two pointers. One is a function pointer to the operator, and the other is the type erased entity. And in our case, when we need to use your thing, we're just going to call, and it's going to be a C call, so it's safe in terms of ABI. We're going to call the function pointer you gave us, and we're going to say, here's the object, here's the entity that was given to us, type erased, and the arguments that we came up with. So let's get a concrete example. Imagine that our session requires a callback, something that occasionally goes and gives you an integer. So the way we do it, we first declare an opaque callback type, session callback underscore T. Everything is extern C, so everything is okay. It's going to work through ABI. Then we're going to declare a function pointer type. This is session caller that is going to be given a type-erased callback and an integer, it's just going to make the call. So it's kind of a dispatcher, very trivial. A concrete example of such thing, so session call here is something that can be provided to session caller type argument. So session call is just going to reinterpret cast the opaque thing to std function. And this is user's std function, not our std function. So it's std function void int, and you just call the callback with the given value. Okay. So if our side needs to make the call, it's going to look like that. First, we ask you to register this. So the register is still on the public side. It's a method on session. We say, yeah, well, give us a lambda or give us a std function of int. We're going to store this as a member of the public session. And it's totally fine because this is only for your compiler to see. It knows the correct way to handle this callback. And then we're going to call the C layer and say, okay, you see this session, you need to register this callback, and we type erase it with reinterpret cast session callback T. And we also provide a pointer to session call, because session call is the function that knows how to handle this. And in the C layer, we're going to do very simple. When you tell us to register, we store it in the session impl at this point layer. We're going to store a function pointer and an opaque pointer, essentially just storing 2 pointers. We don't know how to operate them, but we know that one is a function pointer, so we can call it with the other as an argument. So again, it's kind of like injecting this with C instead of C++. And when the actual call is going to happen, imagine that in our session impl, we have some sort of asynchronous mechanism that occasionally needs to notify the user's of session that an integer happened. And the way we're going to do it, we're going to say this caller, it's a C function. It's perfectly fine to call through the ABI. Please invoke it. Here's a callback, again, type erased pointer to something that only the client side knows. And then we provide our business logic value, which is 2020 in this case. And it crosses the ABI, the dotted line here is the Hourglass ABI boundary. It crosses the boundary and it goes into our dispatch function. And the dispatch function is going to cast this callback to std function. And again, it's client's std function. And put 2020, which is in turn going to call the lambda that was originally provided to us by the client. Okay. So don't call us, we call you. And we call you by essentially binding everything you gave us and then providing the arguments that are part of our business logic. All right. So as I said, vectors or other collections are going to be similar. Just instead of calling a function, we will push back to your vector, but only you know how to push back to your vector. So you will provide some sort of a pusher C function to which you give a type arrest pointer to your vector and the value that is going to be pushed. Again, if it's vector of ints, it's fine. If it's vector of things that are C++ types on their own, there is another layer of indirection. There is another type erasure you need to do, but you can figure this out. And streams I have in bonus slides, and maybe I have time to show you. But essentially, it's very similar. Okay, now even more fun stuff. If your reviewers are like my reviewers, they hate to see naked reinterpret casts. I say that this particular reinterpret cast is totally safe, and the reason is it has a typo. So the compiler will catch it at compile time and say, no, it doesn't work. If you spell your reinterpret cast correctly, then the compiler cannot help you. You say, I know what I'm doing. And well, how often do we really know what we're doing? This is a huge threshold to all sorts of undefined behaviors and nasty runtime crashes, some of which are very hard to debug. So I'm on the same page as my reviewers. I don't want to see reinterpret casts sprinkled through my code. Moreover, I want my casts, whenever they happen, to be checked. So I want to be able to cast only from foo to foo impl and the other way around. And moreover, I want a homogeneous success. So as I said, sometimes we have a handle type and sometimes we have a reference counted types. And in those cases, the opaque handle hides either a raw pointer or a shared pointer, or in the case where you have release semantic, it's something third, it's a reference count block. Okay, this is shared pointer representation. So I want to be able to refer to them in the same manner. I don't have to remember which is which. Okay. So the solution to this problem is obviously template metaprogramming that we all love. So we introduce bidirectional type maps. And we start with a type meta structure, which just contains type defs. We say there is some type opaque that can be converted to impl and back from impl to opaque. And there is also tag. And tag is either raw or ref count. You can imagine other tags like ref count with release semantic or intrusive or any other sort of things. And then we define to impl and from impl. Those are the working horses. Those are going to allow us to, given an opaque type, to produce an impl, and given an impl, produce an opaque type in a consistent way and in a safe-ish way. Now, the actual template definition is slightly longer because we have to be const safe. So if you are giving us a const opaque pointer, you expect to get a const impl pointer or const shared pointer to the object. So because you have to maintain const correctness, you add more traits and it becomes crazy and wouldn't fit on a slide. So you will get it on GitHub, not here. Okay, so now you do specialization, and specialization, what makes things work? You say that to impl for profile T is type meta of profile T, profile impl and raw, and you repeat exactly the same for from impl of profile impl. And then because we have those type defs, if you say to impl of profile T opaque, you get profile T, which is not very interesting. But if you say to impl profile T impl, you get profile impl, which is what you wanted, and the other way around. Similarly, for session, we specialize it like that. We say it's from session to session impl and vice versa, and it's a ref count thing. So be mindful when you convert an opaque pointer, you don't convert it to a raw session impl, you convert it to a ref count object, whatever it is in your system, whether it is a pointer to shared pointer or whether it is a pointer to control block. Okay, this is pretty straightforward, I hope. Nothing crazy with enable ifs, etc., etc. This works and compiles in C++03 on platforms like Solaris and AX. There is nothing crazy going on there. Okay, so uniform access in one direction. So uniform access in one direction, we call this helper PTR, not very imaginative name. And as often with templates, you want to start looking from the bottom. In the bottom, we have something that gets an opaque pointer. So the first thing we do is we try to figure out what is the tag of this opaque thing. So we do toImpl opaque tag, and this will tell us whether it is ref count or raw. Depending on that, we're going to dispatch either to the first function or to the second function. If it is raw, then it is first function, and all it does is reinterpret cast to, well, impl star. But if it is the other kind and we use the release semantic, then it's going to cast it to control block. And then it's going to say, yeah, please return the actual object that this control block points to. And because shared pointer representations are type erased, we need to tell them which type originally the object was. And then we return a pointer to the actual, well, let's say, session, which can be used, etc., etc. Of course, we also have operator arrow and everything else, and lots of helpful things. In the other direction, it's even simpler because you don't actually have to dispatch. In one case, you will get a pointer, raw pointer. In the other case, you will get a shared pointer. So the overload will work fine. We call them both release, and in one case, we just cast your pointer to the opaque pointer, and in the other, we do the release semantic tricks where we say, aha, you gave me a shared pointer, you're no longer an owner of this shared pointer, so should be mindful about that. We're going to destroy the shared pointer, we're going to do release, and then we're going to cast this particular shared pointer representation to opaque pointer, and this is what you get. Okay. Now this can save you in many cases, but you can still outsmart it. So in our real code, we have plenty of static asserts that can check that your conversion makes sense in a static way. We also have some runtime checks that can validate in debug only, because obviously you don't want to pay every time you access a pointer for a runtime check. But they can, to some extent, validate that you're doing something reasonable. Where you can do unreasonable things is, for example, if you decide to reuse opaque types for unrelated classes. You shouldn't do it because they don't cost you a thing. Just slap a new name on a new class. But you have foo and bar, and you cast them both to X, there is no way to go back. In fact, if you had something like this, you couldn't specialize the templates because you would lose the one-to-one, which means that you would use maybe the helpers for one of the types and use naked reinterpret cast for the other. So this is something to notice. This is a code smell. Another thing that occasionally you do is you have classes that are related by inheritance, and you say, I'm just going to reuse opaque types. So you have profile, and then from it you inherit profile underscore A, profile underscore B, profile underscore C. Is it okay to cast to the opaque pointer the base? Well, yeah, sure, but what are you going to do on the way back? Which one is it? So you can, of course, cast it back to base and then try and see with dynamic cast, but it's also some sort of smell. So I would say try to avoid this. The problem with this situation is that if you break the one-to-one, we cannot make any guarantees, and you will not be able to use reinterpret cast helpers, and you will have to use naked reinterpret cast, and you will get them wrong eventually. There is another problem where the specialization would probably work and do the wrong thing, in sense it's going to do an undefined behavior. So whenever you have challenging layout, so multiple inheritance with virtual bases, etc., etc., or even this trick where you refer to a particular member of your class through a pointer to the class itself, they're all problematic because they have to deal with offsets, and as we know, offsets are not too friendly to ABI. And in general, the tongue-of-cheek way of talking about this is reinterpret cast will do fine if the beginning of the thing that you're pointing to is in fact the beginning of your object. It is not always the case when you have virtual bases. It is not always the case when you're pointing to a member but still naming it as a pointer to the actual class. And again, to some extent, we can help you with static asserts and with runtime asserts. We simply try to convert it one way and then immediately convert it the other way, and we see if we get the same thing and the same pointer. If we don't, and in those cases we don't, we say, okay, you're not allowed to do this. It's just wrong. You're not getting what you think you're getting, and this reinterpret cast is undefined behavior because you're only allowed to reinterpret cast from a peg pointer to something that was initially there, and with some caveats, base or descendant classes when it's simple inheritance. Because again, in simple single inheritance, when there are no virtual functions involved, the beginning of the descendant is the beginning of the base class. So you can get away with things. Okay. Almost done. We're good. So takeaway. What was all this about? So as I said, unfortunately, we don't have a C++ standard ABI. The only way to ensure that user compiling with compiler X is able to call a function in my DLL that I compiled with compiler Y is to have them go through a C layer, even if my function is C++. So it hides all your C++ behind a C layer, which is syn. There is a bonus, as I mentioned in the beginning. You can port your library to all sorts of things like Python here. And then the user code is going to operate in terms of the public interface. And of course, pay the price in terms of overhead of doing all these indirections. Right. So at this point, because we still have some time, I will go to bonus slides to talk about something. It's not, I'll go back to this slide later when I'm done. This is where you can find my code. It has a toy implementation of the shared pointer. So you can check the release semantics. It has callbacks, streams, it has dispatch table and other things. So in terms of bonus slides, I'm going to skip stream helper because it's pretty straightforward, I hope now. But I do want to talk about dispatch table. So as I said, there is an overhead in using Hourglass, and the most obvious overhead is that even if you have very simple function, it cannot be inlined. It lives inside DLL. It is called through C layer, so you must pay the cost of the call, which is very unfortunate, and in some cases will hurt your performance. But if you have no other choice, if you need to maintain ABI compatibility like we do, you can leverage this and say, okay, you're already playing a lot. So let's add another layer of indirection. And another layer of indirection could look something like that. Imagine you have a huge struct. And in this struct, you write down the signatures or function pointers of all the C layer functions that you introduced. So if you have class profile and session, here you will have function pointer that matches the creator of profile and the creator of session, the copy constructor of profile and the copy constructor of session, etc., etc. So it's going to be as long as your classes are, and I'm talking about the Hourglass classes that are part of the public API. So this is a dispatch table type, and you can declare a dispatch table entry and the size of this table. You declare it here, users, compiler see it, everything is fine, but the actual initialization of this table is going to be done in runtime when you load your shared library. And there are various automatic or semi-automatic ways to initialize it, but imagine that we initialize it manually. So let's say you have your dispatch table and you have F1 and F2, and F1 expects an integer and F2 expects a double. So whenever you load your DLL, you can populate at runtime, like a plugin system. You can populate these particular entries with F1 and F2. Now at this moment, you have the ability to check whether the version that the user compiled with is above, equal, or below the version of the code that you're loading. And depending on the relationship, depending on this order between what they compiled with and what you're linking, well, dynamically linking, you can make certain decisions. You can say, well, it is totally safe for this client because I see that they use a new header. It's totally safe to put inside F1 not the address of the F1 from my DLL, but the address of the fix. So you can, when you introduced a new F1 fixed, you don't necessarily have to make all your users to migrate to the new fix. They can still be using old stuff. Additionally, if you want to introduce some sort of stub to prepare users for feature changes, you can do it through this mechanism as well. And there are other benefits. So for example, you can do a safe call. I said we have strong guarantees in one of the third slides. One of the way to enforce this is we can introduce this macro, which is call f. So instead of calling directly profile create, you say, no, go to the profile create function pointer in the dispatch table and call that. But how do you know if it is safe to call or not? Well, it is safe to call because you're going to check the offset of this particular function inside the struct, and you're going to see if this offset is below the size of dispatch table or not. In other words, you can validate during runtime if you loaded a version of the library that includes this particular function, or if you loaded a version of a library where this is not yet supported. And if it is the later case, you can do whatever you do, either call a no-op function or throw an exception or use some sort of stub. Now, again, it's a check you need to perform. It costs you something, but in many cases, this cost is trivial compared to the cost you already paid by doing the other thing. So it lets you make even stronger guarantees, and it lets you gracefully degrade for users that use very old headers with very new DLLs, or the other way around. So at this point, I think we're done. And let me go back to this slide. So again, everything is there. You can check it out because there were a few slides were just walls of code, and it can be hard for viewing, but check it out later. And thank you. I appreciate it.
Okay, actually, we have 3 minutes. So, may I ask something from our Telegram chat? Mikhail Matrosov asking, is it safe to add a new virtual function to a class in terms of ABI? He always thought it was.
So it's like an overload. If the class is already virtual, and you add a new virtual function at the end of the virtual table, it should be fine. But because the way we work, we're not even going to call the virtual function. The virtual function is going to call some sort of C method, a C function. So we don't care about that part. The Hourglass allows you not to think about ABI compatibility, but the price you pay is, yeah, you added a new virtual method to your private side, you added a new maybe virtual method to your public side, and you need to wire them through a C call. But in general, you will find that on the public side, you don't normally use virtual inheritance. I mean, you do because you want them to be able to mock your classes, but you yourself don't expect them or you to inherit from session or profile. They're just public wrappers.
Okay, 2 minutes. I have no question in the chat actually. So may I ask, is it possible to generate COR? Because I don't want to write everything by hand.
Yeah, this is a question we get a lot in every time we present something like that. We don't have any code generator. It would be possible to have a code generator, but there is a certain danger in it because it needs to understand certain semantic truths. So it can be semi-automatic. You could say, here, look, this is my class, and please generate the C layer for it through some mechanism of introspection. And then you would have to check that it did the right thing. The problem, if you create a new one, then it's trivial to do. If you're modifying an existing one, you need to be very careful to make sure the modification is not breaking ABI. So in case of, for example, intrusive with ID, where you're touching the actual bytes of the object, any such modifications would be difficult. It's the nice thing is you have a stable library. You usually, if you add an Hourglass class, it's once per release, so once per few months. It's not a lot of work. Thank you.
Okay.
For your experience, and thank you, Oleg, too, for good questions and your support. And now we are going to close the conference and switch into Russian. Okay. Спасибо, ребят. Участники увидят еще вас в Zoom. Олег, помоги Сергею перейти в Zoom. Вы можете задать оставшиеся вопросы в Zoom. И пока-пока, до скорых встреч.
Всего доброго.